We now have an opportunity to start Chapter 3, which will allow us to dig much deeper into atomic structure and talk with great specificity about where the electrons in the atom are located. And as you'll see, this is very important for understanding the behavior of the atoms. So the first question I would like to ask you is, what is light? Okay? There are many forms of light, right? Different kind of light bulbs, but what is light itself? If you answer energy, I would agree with you. Light is a form of energy. And because it is energy, it is able to affect atoms. Atoms are made of protons and neutrons in the nucleus. Those are tucked into the middle and they're pretty secure. And then the electrons are around the nucleus and they are moving. And they have extremely small, almost no mass. And so when energy approaches an atom, it tends to be the electrons that are affected by that energy. I'd like to quickly explain a few characteristics of light waves to you. We'll start with the speed of light. Light travels at a constant speed, regardless of what kind of light wave it is, and the speed of light, known as the symbol lowercase c, is equal to 3 times 10 to the 8th meters per second. Okay? The distance between wave peaks, consecutive wave peaks, is known as the wavelength of the wave. And you can see that these two waves that I've sketched have a different wavelength. The one above has what I would call a longer wavelength. The symbol for wavelength is lambda. And this has a shorter below. The below wave has a shorter wavelength. Now, if you were standing here watching these waves go by and they were traveling at the same speed, you would actually see more of the lower waves pass by. And that gives this particular wave a greater frequency. In other words, there are more waves per second that would pass by you as an observer. The wave above, being more spread out, would have a lower frequency. You would see fewer of those waves pass you by per second. So let's summarize. If the wavelength is larger, the frequency is smaller. If the wavelength is shorter, the frequency is greater or higher, but the speed of light is always going to be the same. One last feature on this slide. If you were to compare the energy carried by both of those waves, I wonder if you could think of this in terms of water. The wavelength that is shorter is perhaps in terms of water more choppy. And if you were sitting in a boat, you would get bounced around a whole lot more by the lower wave, the one at the bottom. And so waves with shorter wavelength and greater frequency carry more energy. And all light waves have their own characteristic energy. There are some relevant equations to be found on your equation sheet related to frequency, energy, wavelength, and speed of light. Here they are labeled for you. Please copy these into your notes, and we'll try using them in the next slide. So here is a sample problem. Given the frequency of a light wave at 3.3 times 10 to the 17th seconds to the minus 1, calculate the wavelength and the energy using the equations on the previous page. Pause and check your work when you are finished. Here you will see the problems worked out. Pause here and examine what I've done. Check the units. Make sure that I've done this correctly. One thing I do want to note down here is the energy you calculate using the Planck's constant equation is going to be a rather small number, and that's because it reflects the energy of a single photon. Photons are very small. Normally we're dealing with moles and moles of photons. Here you see the representation of what is called the electromagnetic spectrum. Electromagnetic spectrum, a range of different light types with different energies, frequencies, and wavelengths. If we look at the whole gamut of these, we start with things like gamma rays and X-rays and ultraviolet. I'm sure you've heard of probably most of those. And then at the other end of the energy spectrum, we've got radios and radio waves, microwaves, infrared. And in the middle is this tiny little smidgen of what we call the visible light, which they've expanded down here below for you to take a look at. The wavelength is larger for these waves. Here's the wavelength, and it is increasing. And the wavelength is shorter for these waves. That means if these on the right have a larger wavelength, they have a smaller frequency, and these have a higher or greater frequency. And these waves have lower energy, and these waves have higher energy. I'm guessing you've probably seen the visible spectrum, and you may have heard of it in terms of Roy G. Biv, the colors of the rainbow, from low energy to high energy. On this particular table, it's backwards. It's Vibgyor, not Roy G. Biv. Okay? Kind of useful information here, just for common knowledge, to be quite honest. Since the electrons are such tiny little particles with very little mass, and they're out around the tiny nugget of the nucleus in the center of the atom, the electrons can very easily be moved by light waves, and they can also be displaced by heat energy as well. If a light wave were to impact the electron in this diagram, one of the possible things that can happen is the electron can be moved to a higher energy state, a higher energy level, and be displaced. Okay? That's one of the options that can happen. Now, the electron is not going to stay there. We'll talk about in the next slide. Another possible impact of energy being absorbed by an electron is that if the energy is great enough, the electron can be ejected from the atom, just totally kicked out, so it's not even part of that atom anymore. That's one of the ways that an ion can form, and we talked a tiny bit about ions in chapter 2. So two possible impacts of energy on an atom: move the electron to a different level, or kick the electron out of the atom entirely. At this point, I'd like you to pause this video and go back to the topics page for chapter 3 and find the video entitled Atomic Emission Spectra. Pause this, view that, and then return, and we will talk about it. It's important that you view that first. I hope you noticed in that video that when atoms in the gas state are exposed to some energy in that light box contraption with that skinny little light bulb that is in there, okay, what happens is the different gases that are in the tubes release different light patterns. Those are called atomic emission spectrum. In the case of a small atom with few electrons, particularly hydrogen, the pattern that you see for the spectrum tends to be rather simple, a few lines of color. The origin of those lines of color is the electrical energy pushing an electron up from a lower energy state closer to the nucleus. That requires the energy, and then the electron can fall back down, releasing a light wave. And that light wave has a certain color. If the electron is raised a different level and released, it releases a light wave of a different color. The options for hydrogen are rather limited, and so the visible spectral lines for hydrogen are few. They're only about 3 or 4, and that depends on how good your viewing apparatus is. In the case of a multi-electron atom, what we often see is we see a pattern that has many more lines in it because there are more electron transitions possible that can release many more different values of energy which correspond with a different color. So each one of these downward transitions would represent a different color of light being released. So electron goes from close to the nucleus to farther away. That requires energy. When the electron falls back down closer to the nucleus, energy is released. Next, I would like you to view the other lesson on the Chapter 3 topics page called Flame Tests. Pause this, watch the flame test video, and then tune back in and we'll talk about what you learned there. So let's summarize what you observed in the flame test video. I hope you noticed the different metals release different colors in the flame. It's also interesting how she described the various safety aspects of performing flame tests. I, in fact, have heard of many flame test demonstrations that have gone horribly wrong and can be pretty dangerous. Anyway, that's another topic. So this is all caused by movement of electrons in the atoms. Those different metal atoms have different colors emitted when they're placed in the flame, and this is caused by their different electron arrangements. The important features here are when the atoms experience heat, the energy is absorbed by the atoms and the electrons move from a low state near the nucleus to some higher energy state. And then when they are up in that higher energy state for a brief instant, the nucleus pulls them right back down and they release light energy of some color. And that determines the color of the flame that is seen in that test. This diagram is a tiny bit blurry, I apologize, but it kind of summarizes the things that we've talked about here. The nucleus is in the center of the atom. We have n equals 1, n equals 2, n equals 3. This is how the energy level is noted with an n equals something or other. And electrons absorb energy in moving from a location near the nucleus to farther away. When they fall back down, as is happening here, they release light energy in the form of a light wave. Okay, and each of the light waves that are emitted has a particular color associated with it. So this is a quick summary of really the lesson in this first video lesson for you. The Bohr model was based on hydrogen atoms, which he chose because they're the smallest atoms with the simplest electron arrangement. The concept of what he was saying does apply to other atoms, but his equations, which we have not seen and will not see, do not apply. But we do hold on to the concept that electrons remain close to the nucleus if possible, if we leave them alone, but they can be moved to a higher energy level with some force, particularly energy absorbed. But those excited state electrons will then fall back down to be closer to the nucleus, releasing light energy.